Okay, so in this lecture, I want to tell you about Sylow's theorems. Again, there are 3 of them, like 3 isomorphism theorems. But I think these are really much more interesting than the isomorphism theorems. Sylow's theorem, the whole, sometimes it's called just Sylow's theorem, the whole thing together. This is my favorite part of this course. This is going to tell us something about the existence of subgroups in an arbitrary finite group, actually saying that there are subgroups based on the arithmetic of the order of the group. So when you just start learning groups, and we say, okay, we have a group of order 63, and then it's not clear even, like, does it have a subgroup of order 4? Okay, but then we learn from Lagrange's theorem, no, it does not have a subgroup of order 4 because the order of a subgroup must divide the order of a group. But then, okay, my subgroup of order 63, so 7 does divide 63. 63 is 7 times 9. So does it have a subgroup of order 7? And this is just a very easy special case of what Sylow's theorem tells you. So let's see what it says. So let's make some definitions. So definition, so one that I've already given in a previous lecture, but let's just recall it. A P group is a finite group G such that the order of G is equal to P to the K for some K at least 1. Okay? So it's a group whose order is a power of P. Okay, so Sylow's theorem is about the existence of subgroups of a finite group G that are P groups. Okay, so now we can call this definition A. B, a P Sylow subgroup of a finite group G is a subgroup P such that, so P is a P group. So say the order of P is P to the K. And then secondly, it should have the largest prime power order that also divides the order of G. So we want to assume that P to the K divides the order of G, but P to the K plus 1 does not divide the order of G. Okay? So in other words, the order of G is going to be P to the K times some M, with M relatively prime to the order of G. Okay. So Sylow's theorem is about the existence of P Sylow subgroups, the number of them, and their structure. So theorem Sylow. So part 1 says Sylow subgroups always exist. So if the order of G is P to the K times M with P relatively prime to M, then G has a subgroup of order P to the K, i.e. G has a P Sylow subgroup. To make this non-trivial, we should maybe assume here that K is at least 1, so that P is really dividing the order of the group. Good. So this is already very surprising, right? So I have a group of order 3 cubed times 17 times 23. Well, 3 cubed divides the order of this group, and 3 to the 4th does not. I know it has a subgroup of order 3 cubed. And you think to yourself, how are we ever going to construct that? But it does exist, and it's actually not too hard to prove its existence. Secondly, assume P is a P Sylow. So often we stop writing P Sylow subgroup and just P Sylow of G, so the P Sylow subgroup of G. And Q is a P subgroup of G. So by this I mean that Q is a P group, and it's a subgroup of G, but it might not be a P Sylow. It might be a P Sylow, but it might not be. It might have order P to the J, where J is less than the largest possible K. Then there exists G in G such that GQG inverse is contained in P. So what is this saying? Well, in particular, important special case to remember, in particular, all P Sylow subgroups in G are conjugate in G. Okay? So if you take a P Sylow subgroup and you conjugate it by some element of G, then it's easy to see that you get, again, a P Sylow subgroup, because conjugation is an automorphism. So in particular, you conjugate a subgroup of order n, you get another subgroup of order n. And the property of being P Sylow is completely given in terms of the order. But what is not clear is that if you start from one P Sylow and you conjugate by different elements of G, you will actually hit all the other P Sylows of G. That's what this statement is saying in the case that Q is another P Sylow. To get this in particular, take the case where Q is another P Sylow. Okay. So this was part 2. And part 3 is perhaps the most surprising one. This is saying something arithmetic about the number of P Sylows. So let NP equal number of P Sylows in G. So by part 1, we know that NP is not 0. But in fact, we know much more. Part 3 asserts that NP is congruent to 1 modulo P. And a kind of second thing to complement this is that also, and this is by now follows from 2, that NP divides the index M of any P Sylow P in G. So we were writing the order of G as P to the K times M. A P Sylow by definition has order P to the K. That means that its index in G is M. I'm saying that this number NP, in addition to being 1 mod P, it also divides M. Okay. Okay, so now that we have seen the statement of Sylow's theorem, let's begin to see the power of this theorem in action by doing some applications. So applications. So here is one. There is no simple group of order 12. Okay, so recall G is simple if the only normal subgroups of G are the identity subgroup and G. Okay? So why is there no simple group of order 12? So these arguments usually go by assuming that there is such a group and deriving a contradiction. So assume G simple order of G equals 12. So by Sylow 1, G has a 2 Sylow P and a 3 Sylow Q. Now what can we say about these? To say things about them, we have to use Sylow 2 and 3. So by Sylow 3, the number of 2 Sylow subgroups, remember I'm using, as in the statement of the theorem, NP to mean the number of P Sylow subgroups. The number N2 of 2 Sylow subgroups, this is congruent to 1 mod 2, and it divides the index. Now, what's the index? So this P Sylow subgroup P, so the order of P, it's the maximal power of 2 dividing 12. 12 is 2 squared times 3. So P has order 4, and Q has order 3. This 2 Sylow, it's congruent to 1 mod 2. The index, it has order 4, so its index is 3, and N2 divides 3. Well, this doesn't leave so many options. This implies divisors of 3, there aren't so many. 3 is prime. So this means that N2 is either 1 or 3. Okay? But a general consequence of the Sylow's theorems, so in general, NP equals 1 if and only if the unique, because NP equals 1, is normal. This is follows from Sylow 2. Okay? Because if I have a unique P Sylow, and we call it P, now I conjugate it by an element G. Okay? I must get P, otherwise I would get another P Sylow. We said every conjugate of a P Sylow is a P Sylow. So the fact that there is a unique P Sylow says that it is normal. So I have this situation, N2 is 1 or 3. So by what we just said, if N2 equals 1, this P Sylow is unique and normal, then P is normal in G, contradicting the simplicity we found a non-trivial normal subgroup. Okay, so we must have n2 equal to 3. Now let's look at n3. Again by Sylow 3. n3 is congruent to 1 mod 3, and n3 divides 4. This implies that n3 equals 1 or n3 equals 4. So again, n3 equals 1 implies Q normal in G, contradiction. So we must have n3 is equal to 4. So this is the first step, and you will do a lot of these in homework, and you will see a lot of these arguments. The first step to do is to try to understand what these NPs are. How many P Sylows are there? And this is, I've started with a simple example. In this case, we have completely determined these numbers. N2 must be 3, and N3 must be 4 if the group is to be simple. What do we do next? We want to count elements. Count elements. What do I mean by this? Let's look at these 3 Sylows. So Q is a 3 Sylow. The fact that it has order 3 and 3 is prime, any group of prime order is cyclic. So this implies that Q is cyclic of order 3. Okay, now, so this implies that Q has 2 elements of order 3 because it's cyclic of prime order. It means that any non-identity element is a generator, that is, has that prime order. In this case, this means we have the identity and we're left with 2 elements of order 3. Now, the other thing to note is that if Q1 and Q2, we are assuming that we have 4 3 Sylows. If Q1 and Q2 are 2 3 Sylows distinct, then Q1 intersect Q2. This must be the identity. Why? Because the intersection, it is a common subgroup of both Q1 and Q2. So its order must divide the order of Q1 and the order of Q2. So the order must divide of the intersection must divide 3. So it's 1 or 3. But because they are distinct, if their intersection has order 3, it means they're equal. So they're not distinct. So the intersection must have order 1. So these two things together say that if we look at our 4 3 Sylows, so conclusion, for our 4 3 Sylows account for, so we have 4 of them. Each one has 2 elements of order 3. And no such element of order 3 appears in 2 of the 3 Sylows, because that would mean a non-trivial intersection. So this gives us 4 times 2 equals 8 non-identity elements. Now, if I have P1 and P2, if P1 and P2 are distinct 2 Sylows, then the cardinality of their union, what is it? So in this case, the order is 4. We can't use this argument about prime order. P1 and P2, they might intersect in the identity, and they might intersect in a subgroup of order 2, which divides 4. But this cannot have 4 elements, because that would mean that they are not distinct. So their union, because they're distinct, there must be something in P2 that's not in P1. That means that this has strictly greater than 4 elements. Now, these elements here of order 3, they're nowhere to be seen here because these have order 4. You cannot have an element of order 3 in a subgroup of order 4 by Lagrange's theorem. So hence, G has at least 8 elements from the 3 Sylows, 8 non-identity elements, plus at least 5 elements from here. And that's really absurd because G had order 12. Okay? So that concludes our proof. Note that what we really showed here was that if the 3 Sylow was not normal, then we have 4 3 Sylows, and that forced us to that we could not have 2 distinct 2 Sylows. So what we have really shown is that we have shown the stronger statement that either G has a normal 3 Sylow, or if not, we cannot have these distinct P1 and P2. It means we have to have a unique 2 Sylow P, and then by the general remark, if your P Sylow is unique, it's normal. So either G has a normal 3 Sylow or G has a normal 2 Sylow. Okay? So in more complicated examples, we might not be able to show that G has a normal P Sylow for some prime P. We might be able to conclude for some more sophisticated reason that G is not simple, but here we're actually able to show not only does G has a non-trivial normal subgroup, it actually has one either of order 3 or of order 4. Okay.